So good morning, everyone, and welcome to Microgrid 201, Thermal Technologies. I'm Lulu Arias, I'm the Director of Customer Success here at Xendee, and I'm joined by Rita Chen, one of our Customer Success engineers. This is our agenda for today. I'll be handling part 1, covering the why, the what, and the how of thermal integration. So first, we'll discuss why thermal technologies matter. Then we'll review what is thermal energy in microgrids. And finally, I'll show how to model thermal systems in Xendee. After that, Rita will take over part 2 and lead a live interactive modeling example in Xendee, showing you exactly how these inputs translate into an optimized design. But before jumping in, let us introduce ourselves. I'm Lulu Arias, as I mentioned, Director of Customer Success here at Xendee. Before joining Xendee, I used to work as a consultant at Boston Consulting Group. There, I led different teams, but mainly focused on mining and oil and gas. After that, I did my MBA, and I decided that I wanted to transition into green energy. And that's when I joined Xendee almost 3 years ago. And ever since then, I've been working closely with the customers, helping them model their microgrids. Rita, I'll let you introduce yourself.
Hi, everyone. Thanks for joining us. My name is Rita. I'm a customer success engineer with Xendee. Prior to joining Xendee, I used to work in surface hydrology, where I also helped scientists and engineers alike with their technical applications. I joined Xendee about 2-ish years ago, where I've been working closely with customers as far as making sure they have the best experience with Xendee and helping them troubleshoot. If you're one of our current users and ever submit a technical support request to us, I'm probably the first person taking a look at it. At Xendee, I also work closely with Lulu to make sure that our users have the best experience they need, take all of your good feedback, and then also host educational events like these webinars and trainings. Yeah, thank you.
Thanks, Rita. So let's get started. Clients' requests are pushing us to model systems with thermal heat and CHP. When we properly integrate and model the thermal side of a project, we unlock 3 fundamental value propositions. First, there's an opportunity for system efficiency and cost effectiveness. If you only manage the electrical load, you fundamentally leave energy and money on the table. By capturing the waste heat a generator produces, you significantly increase the total energy utilization of your fuel source. And this pushes overall efficiency from 30-40 up to 70%. Second, there's enhanced system resiliency. So resiliency must extend beyond simply keeping the lights on. So thermal systems, mainly through CHP and backup boilers, ensure you maintain essential heating and cooling capabilities. This is very critical for facilities such as hospitals, data centers, and industrial operations during outages. And finally, using multi-energy technologies reduces the reliance on traditional fossil fuels for heating and cooling. So this integration, where technologies like CHP interacts with chillers, boilers, heat pumps, introduces significant modeling complexity. We have to balance competing energy streams and manage heating, cooling, and electricity simultaneously. This is precisely why Xendee's multi-energy optimization is critical. And we'll see this in more detail in a couple of slides. So this kind of sets the stage for the rest of the technical discussion, so let's get into it. In simple terms, thermal energy refers to the heat used for comfort and operations, space heating, water heating, process heat, cooling, and refrigeration. So the critical point is that a microgrid, as defined by the DoD, is a group of interconnected loads and DRs within defined boundaries that acts as a single controllable entity. This includes both electrical resources like PV, batteries, and thermal resources like CHPs. Therefore, a true microgrid must manage both electrical and thermal energy flows. This integration, especially through CHPs, which simultaneously produce both electricity and useful heat, is the primary driver for achieving the highest possible system efficiency. Well, I know this is a complicated diagram, so let me quickly walk you through what you're seeing. It's an energy flow diagram showing all the energy streams in a typical microgrid. Let's look at the main sections. So at the left, we have the different energy purchase choices, like buying power from the grid or purchasing natural gas. At the top and bottom of the center, we see all the energy sources and local storage, the equipment on site that generate and store the energy. And finally, on the right, we have the end-use equipment, where all the energy actually gets consumed. So this diagram uses arrows to show the actual energy flowing, and colors matter. So we have blue for fuel, green for electricity, and red is waste heat. If you look at the CHP unit, which is at the bottom, it consumes fuel, blue, and produces electricity, green. But the critical part is the waste heat, red, that it produces. Now is where the system kind of gets complicated. These technologies don't just work in isolation. They compete and cooperate. For example, to provide heating, your CHP can produce heat from its waste. A traditional natural gas boiler can also produce heat. A heat pump can use electricity to produce heat too. So as soon as you introduce multiple technologies, the links become incredibly sophisticated. The choice of which one to use changes every minute based on factors like the price of grid electricity, how much solar PV is generating, the actual demand for heating or cooling. So sometimes you might run the generator at full load and charge your batteries, not because you need electricity right now, but because you need waste heat that it produces to meet your thermal load. So it's not always electricity that drives the decision. So this complexity, where all these energy streams must be carefully balanced, is exactly what the Xendee multi-energy model is designed to optimize. Let's dive then into Xendee. So, as you know from working with electricity, we need detailed load profiles to do a good analysis, especially since they can be very volatile. So thermal loads are no different. If you don't have this consumption data, there's ways in Xendee that help you create or gather it, or you can simply upload your existing files. It's essential to categorize these thermal loads accurately because they are a substantial and highly variable portion of the facility's total energy demand. These loads include four main categories: space heating, which is to maintain comfort levels in buildings; domestic hot water, which is also a demand found in most facilities; process heat, which is the thermal energy required for specific industrial processes; and cooling demand, air conditioning for buildings and dedicated cooling for data centers. So we use these four thermal loads to define the demand. Now, let's take a look at the generation side. So we're going to dive into specific thermal technologies and explain in more detail how to define them in Xendee. This background will ensure you understand exactly what Rita will cover in the next section of our webinar. Great. So the anchor technology for any sophisticated multi-energy design is a CHP. In Xendee, defining the CHP is straightforward, but inputs are key to accuracy. So first, we capture investment and maintenance cost, as with all our technologies. Then you specify the fuel type, whether it's natural gas, biofuel, hydrogen. Then we have the nameplate efficiency that can be set to a constant value for a maximum accuracy. You can also enter detailed non-linear efficiency curve. We also have a temperature derating, which by default, the output power percentage is 100% at all temperatures. But same as with efficiency, you can enter a nonlinear temperature derating curve. Next, we have the heat to power ratio. This is the ratio of useful heat produced for every kilowatt of electricity. You can set a single value or again, use the non-linear curve. For example, right here, we have a ratio of 1.426, which means you get 1.426 kilowatt of heat for every 1 kilowatt of electricity. Finally, to activate its thermal capabilities, you simply toggle CHP to yes. We also offer a heat curtailment toggle, which when set to yes, allows you to model away excess heat when there's no thermal demand. And well, it's important to keep in mind that while we're focusing on the CHP specific settings here, these generators like the CHP generators also have the standard non-CHP specific parameters that you're already familiar with. So this includes minimum and maximum load constraints, setting ramping rates to ensure that the model accurately reflects the physical limitations of your generator. So cooling represents a major energy load, and chillers are the key suppliers. We look at two types, electric chillers and absorption chillers. In Xendee, we model all chillers using the coefficient of performance, or COP. The COP is simply the ratio of useful cooling output to the energy input required to run the system. A higher COP is more efficient. So electric chillers use high-grade electricity and have a high COP, typically between 3.5 to 7. Absorption chillers are different. They use low-cost waste heat and have lower COPs. A simple single-effect absorption chiller will always have a COP below 1. You only see a COP above 1 when you are working with more complex double effect or triple effect chillers. But regardless of the number, the absorption chiller's true value is not its numerical COP. It is its ability to turn low-cost, wasted heat into valuable cooling. This synergy makes the overall system more economical. In our model in Xendee, we use both a COP and a temperature degrading curve, which models how the chiller's performance decreases as the temperature increases. Boilers are technologies that burn fuels like natural gas or propane for direct heat generation. Their primary role in a microgrid is to serve as baseload heating or as backup heat source. Xendee models them using a nameplate efficiency, which is typically higher, around 90%, and fuel type. Heat pumps offer great value because of their high efficiency and versatility, and they can provide both heating and cooling. So air source heat pumps typically have a COP of 3 to 5, and ground source heat pumps are more effective because of stable ground temperature, leading to higher COPs, usually ranging from 4 to 6 or even more. So in Xendee, the primary inputs are separate heating and cooling COPs. These values too can be customized for nonlinear curves to account for temperature variation in the real world. And finally, thermal storage is equivalent to an electrical battery, but for heat or cooling. It stores thermal energy for later use through methods like water tanks or ice storage. So the critical value is its ability to shift heating and cooling loads and reduce peak demand. By using cheaper off-peak electricity or excess thermal energy to charge the storage, and then discharging it during expensive peak hours, it significantly enhances the financial performance and integration of all other DRs. So modeling thermal storage allows Xendee to capture this time of use rate arbitrage for thermal loads. And here, well, we also have the heating and cooling COPs as inputs within Xendee. So finally, this comparison table provides a high-level view of how each technology fits into a microgrid strategy. So CHP has high efficiency, 60 to 80%, and is the clear choice for sites with large simultaneous heat and power needs. Boilers offer low to moderate cost and reliable backup heat. Absorption chillers are valued for waste heat cooling. Heat pumps have the highest flexibility and high efficiency making them an excellent choice for sites needing both heating and cooling, and they pair well with solar PV. Thermal storage is valued for its flexibility in enabling demand shifting and improving the economic integration of every other DER. So this kind of illustrates the strategic importance of selecting the right thermal mix for your project's objectives, a selection that Xendee optimizes and simplifies, as you'll see with Rita in just a minute. And as we conclude this first part of the presentation, let me summarize the most important key takeaways. Thermal technologies unlock cost savings and improve overall efficiency. Thermal storage allows shifting demands and reducing peaks. And only by modeling thermal and electric systems together, we can achieve a truly optimal microgrid design. This integrated approach is the core of what Xendee delivers. Having said that, I'll pass it over to you, Rita.
Great, thank you for a great introduction, Lulu. Okay, so the second part of this live course is going to be kind of a follow along demo that's going to be in Xendee. So yesterday, when you got the informational email for this course, you should have gotten information on how to log in to your 1 week demo trial account. If you are a previous user, you should have just been, or previous or current user, you should have been able to just log in. And then if you are a new user, completely new to Xendee, you should have gotten a temporary password with the email that you signed up with. So I'll give everyone a moment to pull up their Xendee account and log in. And what I'm going to do is I'm going to share my screen so we can do a follow along Xendee modeling exercise. Okay, again, I'll give everyone a moment to pull up Xendee. You should have also gotten a share project from me. You can either see it through when you log into Xendee, you'll see a folder that says share project by Rita Chen, me, or you should have gotten a separate email, again, to your same email address as your login that says Rita Chen has shared a project with you. Click on this link to view it. And it should be called a thermal demo hotel base. And this is going to be the project we are going to be working off of for this demo portion. This demo portion is meant to be interactive. So if you would like, please follow along as I go through every single step, explain every single step, and you can replicate my instructions on your own project so that you also get the full experience of modeling, going through the process of adding all of our technologies and interpreting our results. And of course, if you have any questions during this part, feel free to type it in the chat where my colleagues will be monitoring and answering as we go. Okay, so let's go ahead and get started. So hopefully everyone has this project pulled up. This project is a generic hotel based in Georgia in the United States. As you can see, I've already set up a few components of the hotel. For the sake of time, we are not going to actually make a model completely from scratch. If this is your first time modeling with Xendee, just know that we are skipping over a lot of fundamental steps in the modeling process. If you want to learn more about modeling from the very beginning and kind of the more basics, we have some helpful guided walkthroughs on our help center, as well as our Microgrid 101 recorded video. Remember, this is Microgrid 201. We do have a 101 that goes through the very basics as well. Okay, so let's go over very quickly what is already set up. So first, if you click on the top here, this main tab, you're going to see that we have a settings chart. And usually the settings chart is where you can review your project information. In this case, we have our name, project location. We also have settings for our units, and that also pertains to heating and cooling units for reporting. The default is going to be kilowatt therms, but of course, if you use other units like BTUs or therms, you can use that. but I'm just going to leave it as a default kilowatt therms for now. And of course, when you set up a project, you can change the currency and project year, but I'm just going to leave it as this for now. We're not working with multi-node this time, so we're going to leave it as no, to leave it as just a aggregated one single node project. And we are grid connected because we are going to be utilizing utility electric purchases. And then when you scroll down, you'll see that you have all of the technologies listed out for your project. And this is simply just a options chart for actually enabling the ability to add these technologies. This doesn't mean that these technologies have already been added to your project. It just means that I'm enabling the icon to be added. So I have the basic ones enabled, like solar, battery energy storage, EV charging, but we're not going to touch that today because we're focusing on thermal technologies. So then under multi-technologies here, you'll see I have generator enabled, which is going to include CHP, combined heat and power generators. And then you'll see under heat technologies, I have boiler enabled because that's what my project already has. And then we also have cooling technologies enabled, such as electric chiller, absorption chiller, and cold storage, which we are going to be working with today. So if you want to add another type of technology to your model, you can always enable it here so you can see the symbol pop up. And what I mean by that is once you enable those technologies, in the bottom of the page, you'll see a symbols tab. If you click on the symbols tab, you'll see all the technologies that are enabled in the settings page. Again, this doesn't mean that they're already actually in your model. They just enable the symbols to appear in the symbols tab so that you can actually add it. Okay. So let's first go over what I've already added to your actual model. So first, let's click on the load symbol. So see right now, we only have the electricity load added, which is just going to be a representation of our site's electrical demand. We are going to have to add our thermal loads, so we'll come back to that in a little bit. But just for the sake of saving time, I've already added electricity. And if we go over to the top left corner where all these tabs are and click on electricity, click on this electricity tab, you'll see that this is where we usually set up our electricity tariff. So the tariff that you have contracted with your local utility provider, so you know how much to pay them for electricity that you buy. Normally, of course, you will also have to set this up in detail so Xendee can know how much to pay for your electricity charges. But for this one, I've also already set up a time of use tariff. So by time of use, what I mean is that during different time periods throughout the day, the electrical charges or the electrical rates are actually going to be vary. So during some hours, like the evening hours, it's going to be more expensive to buy electric utility. And then some hours, like the off hours, you know, early morning, late at night, it's going to be the cheapest to buy electric utility. I've already defined it here as period 1, period 2, and period 3. As we can see, period 1 is most expensive, 25 cents per kilowatt hours, whereas period 3 is the least expensive at just 8 cents per kilowatt hour. And then in the table TOU definitions, I've defined period 1, 2, and 3 for our different day profiles. But generally, period 1, which is the evening hours, is going to be most expensive. Don't worry if you are a little bit lost on the tariffs. It won't matter too much for us as far as this demo, but we will also see how it reflects in the final reporting. So we can cancel out of this. And you'll see the rest of these tabs here on the left-hand side. Usually you should also make sure you have all of them set up if you are going to utilize them. We will come back to the fuel tab because we will be reviewing our fuel resources later for one of our technologies. The rest of these we're just going to leave as a default for now. But of course, if you have other microgrid components that you want to change, like outages or different financing strategies, you would also have to take the time to input those. But just know, for the sake of this demo, we are just going to be sticking with the basics. Okay. So now let's go back to our load icon and set up our thermal loads. So again, click on this load icon, double click on it. And what we're going to do now is we're going to enter in our thermal loads. So if you are familiar with Xendee or other microgrid modeling management software out there, of course, we all have to set up our load profiles. In Xendee, there are several ways you can do that. If you have your historical time interval data, whether that's 8760 or 30-minute, 15-minute interval data available, you can directly upload it with our enter load shape file, and that allows you to just directly upload a CSV. If you don't have the load shape available because, whether you have a site that doesn't have that information available or new construction site, we do have several options for estimating a load profile as well. And what we're going to use today is the NREL load shape tool. So click on the NREL load shape tool, and you'll see here, it's already pulled up a common load profile that I've picked previously. But if you actually go back and to the bottom here, hopefully you can see it, it's at the very bottom of the page, and click on change city, you'll see that what I've done in the previous step is I've picked a city that kind of falls within the same climate zone as my site, which I just happen to have the exact one. It's Atlanta, Georgia. And then once you click on this, what NREL provides is it has a catalog of kind of common industry average load profiles for different building types. In this case, I've picked a large hotel. That's going to be a newish construction. And we are going to be entering both our cooling and heating loads. So what we're going to do here, and you might see it filled out already here, is I filled in kind of the approximate annual consumption for chiller use, as well as the annual peak demand. And then on the right-hand side, if you click on cooling tab instead of the electricity tab, you're going to see that profile populate based on the numbers I put in. Now, I just use the typical default numbers, but of course you can scale it to, whatever consumption your site may have. A lot of times people will only have historical 12-month bills that only has the consumption and peak. So this is where you would enter it if you have data like that. And then I'm also going to import in space heating and a water heating profile. So that's why I've also filled in natural gas here as well. And then if we go over to on the right-hand side, the space heating and water heating tab, you'll see that these have also been generated / calculated. And then at the very bottom here, you'll see that I have enabled them as load shapes to import. So this means that I want to import these load shapes into my site. So again, if I don't have cooling or one of them selected, it's not going to bring it into my model. And I am going to ignore the other ones because we're not dealing with refrigeration or natural gas this time, but just know that these are options as well. So once you have cooling, space heating, and water heating selected, let's go ahead and click on Import Load Shape. And then what this is going to do is it's going to bring those additional load shapes into our building load profile details. So then you'll see here, before we only had electricity, but now we also have our cooling, space heating, and water heating. And beneath that, you'll see we also have the different tabs where you can review the different load profiles. And it also breaks them down by typical weekday, typical weekend day, and typical peak day for every month. Again, we have the same for space heating and water heating. Now, your site may not have both cooling and heating, when you're actually working on your own projects. That's totally okay. We're just going to cover both today. So then once you've done that, at the bottom left-hand corner, it's very important that you click save. If you don't click save, you're going to lose your progress. So be sure to click save. Okay, great. So hopefully everyone is caught up. Just as a recap, all we've done so far, all the changes we made so far is just importing the cooling, space heating, and water heating profile using the NREL load shape tool. Okay, so now let's move on to our DERs, or our distributed energy resources. So as you can see in the model, I've already added in a boiler and an electric chiller. So let's go over both of these so far. So I added them in as existing assets. So that means that they're already on site, and that's how the current heating and cooling load are being met. And if you click on them, you'll see that we have our boiler, and you can always rename it to be more specific. Like I'm going to make it here, existing boiler, just so we know that it's already there, it's already existing. And then under the technology decision, what I've done is I have set it to existing, and this just tells Xendee that this asset is already there, it's already paid for. And I have defined the existing size as well as its existing age. Age matters just because if you have a lifetime example, for example, if it's shorter than your project length, then that means it's going to need to be replaced. And usually you will have to define your investment specifications, any maintenance costs, which I've done already. I've also defined the technical specifications. For boiler, it's pretty straightforward. You just have to define the nameplate efficiency as well as a fuel type. So the fuel type, you'll have to define or choose from a dropdown. So as you can see, we have kind of the typical gas or fuel types available, as well as a custom fuel. For this case, we're going to use natural gas. Okay, and then let's save and exit out of this. And we have fuel selected for our boiler, but we need to actually define our fuel characteristics because remember, Xendee needs to know the cost of buying everything, including fuel for your optimization. So we need to define how much that actually costs. So this is where the fuel tab on the left-hand side will come in. So on the left-hand side here, remember we have this fuel tab. So let's explore this really quickly. So here you'll see the fuel settings for all of the different default fuel types, as well as the custom fuel available. Now, one thing to note for the boiler and its natural gas usage is that there's going to be two natural gas options at the top. So you see we have the natural gas fuel purchase for basic services, as well as the natural gas fuel purchases for on-site generation. So it's a little bit confusing, but the boiler one is actually going to be using this one on the left here, the natural gas for basic services. And this natural gas for on-site generation is going to be for generators that use natural gas. So that would be like our typical generators, our CHP generators, our fuel cell generators. So if you are changing the fuel fee or emission factors or annual limits for one of your technologies, you have to be sure to change it under the right fuel type. But for this one, we're just going to leave it as a default. Okay, so now let's talk about our electric chiller, which is also one of our existing assets. And I am going to rename it as existing electric chiller, just so we know that it's already there and that's what's currently meeting our site demand. And again, under the technology decision, I have set it as 100 kilowatt capacity and its age as well. Same thing below here, we have to define our technical specifications and its coefficient of performance, which as we remember, it's the amount of chilling it can output for every unit of electricity that it uses. And we're not going to change anything for the chiller for now. So we can exit out of this. Oh, just kidding. I need to save my name. Existing electric chiller. Okay, so now we have both of our existing thermal assets. Let's run an optimization first, just to see what our current baseline looks like. So at the very top of the main tab, we're going to click on Optimize. So here you have to type in a name for your optimization. I usually try and keep it pretty descriptive. In this case, we are just going to be looking at the existing baseline. So I'm just going to call it baseline. Everything else here, we can just leave as default. Under optimization decision, I'm going to click reduce cost because that is my goal. Of course, if your goal is to reduce emissions, you can turn that toggle on instead of reduce cost. And then here under reference model, for the reference source, it really doesn't matter here because we're just looking at the baseline. You can either do Xendee computed, which is going to also compute a base case with your existing baseline. But we are looking at our existing baseline right now, so there's going to be no difference. Or you can do no reference scenario, which just means that you're not going to be comparing it against anything when it comes to savings or emission savings. I'm just going to leave it as a default. Don't worry too much about that. And then the analysis fit configurations, we're just going to leave off for now, but of course, feel free to explore those later. And then once you're ready, you can run an optimization. And you'll see that on the top right, it is going to start our analysis. And it shouldn't take very long, and I'll let everyone take a few seconds to, hopefully catch up. Just to summarize what we've done so far, what we've done is we've added our thermal profiles to our load icon. And we've also just taken a look at our existing setup, which is our existing boiler and existing electric chiller to see what they look like in Xendee. Of course, the existing boiler is going to meet our heating demand that we've set up, and the existing electric chiller is going to meet our cooling demand. Okay, and once your project completes its optimization, all of the results are going to be under our results tab here. But you'll also get a notification when it completes, and you can directly click on the results from here, show optimization results. So let's go ahead and click on that, or you can get it from the results page. So you'll see that our report at the top is not going to have much news because we are just looking at our existing baseline. Remember that the reference scenario is our existing baseline, so the numbers are going to look the same. We are not going to have any new investments in this run because, again, we have not added anything new yet. So let's scroll down and kind of go through where our technologies are being used. So the summary tab is just going to have some summaries about where your system costs are coming from. As you can see, we also have a cost and savings table, and most of the years it's just going to be OPEX, so your operational expenses. And then at year 15, we do have to replace our existing electric chiller because its lifetime is going to run out by then. So we have to get a new one. So that's why there's that bar there. If we go to the financial data tab, we'll also see our microgrid cost breakdown. Again, in this optimization, the base case and optimize are exactly the same because we're just looking at our baseline. But you'll see most of our costs are going to be the blue bar, which is electric utility purchases, and then some in the black bar, which is fuel. If you go down to our cash flow table, you'll see a detailed breakdown of our costs item by item. So here we have our utility demand charges and energy charges, which is the money we're paying to get our utility electricity. We'll also have a line item for fuel purchase costs. So those are our main operational expenses. And then if you go down, you'll see that we have our replacement costs for our electric chiller. And then let's go to our utility data tab. So you'll see we have some charts at the top that break down our monthly demand, our consumption, as well as charges. Remember that we only have one period defined for our electricity. So that's why they're all the same period. And then the monthly energy consumption, you'll see that we have this broken down into electricity and natural gas basic, which remember is a fuel that we need for our existing boiler. And then we also have the utility charge breakdown into energy charges, demand charges, the fee, as well as a fuel cost. And then if you scroll all the way down, you'll see that we also have this extra section dedicated to fuel charges, which is going to be where our fuel for our boiler comes in. Now, we are just going to be going over the thermal part of this report, but I highly encourage you to actually take the time to explore every single part of the report on your own time, especially if you are a new Xendee user, because there's a lot of information that goes into these reports. So let's take a look at our energy balance and technology investments chart. So at the top here, we always have some charts dedicated to the electric and utility, but let's scroll down to where our thermal demands come in. So now you'll see that here under aggregated demand, we also have all of our thermal profiles. So we have our electricity, cooling, space heating, and water heating. As you can see, cooling is the biggest of our demand. And then we also get these pie charts that break down our heating balance and cooling balance, as well as our generation technologies. Now let's go to our dispatch by end use chart. And this is going to be where you can visualize and see how each of our load profiles are being met. So of course, we always have our electricity dispatch. And as you can see, it's all being met by electric utility purchase because that is our only electric source right now. And you'll also see that there's a second dash line, this dash blue line at the top, and that's going to represent our electricity need for chilling. So this is going to be calculated in addition to the electric load profile that we uploaded. Because remember that our electric chiller is driven by electricity, so that in turn, it will create its own electricity demand. So that's why you see two kind of line profiles here. We're going to have one for the load that we actually uploaded in our load icon, and then one that's generated as a result of the electric chiller being used. And of course, with these demand charts, you can change it by month. as well as the day type, so weekday, peak, or weekend day. And now let's take a look at our heating dispatch. So the heating dispatch is going to correspond to the heating loads that we entered. Remember that we enter both a space heating load and a water heating load. So that's what those two dashed lines represent. And of course, they're all going to be met by our existing boiler. And let's take a look at our cooling dispatch. We only have one cooling load, so that's what this black line is going to be. And of course, we only have our existing electric chiller, so that's going to be the sole provider for our cooling load. And then lastly, we have our operations summary tab at the top here, which is just going to have some kind of summary metrics about our technologies. So here we just have emission summary, as well as a technology capacity factor chart. This tab, or the contents that go into this tab, will also change depending on like what technologies you have added in your model. So for example, if you have like a battery energy storage, you'll also get additional charts related to battery. And then lastly, we have our print report chart, which you can use to customize and then download your report into a printable PDF. Of course, you can try this out later if you like, but we're going to skip this for now. So that is our baseline scenario. So what it currently looks like, our business as usual case for our little demo hotel here. So now that we understand what its current operation is like, we can now add new DERs, or new distributed energy resources. So first, what we're going to do is we're going to add a generator, but we're going to first add just a regular generator, so not a CHP or cogeneration generator, just to see what adding a regular generator would be like. And then after we add our regular generator, we're going to convert it or switch it into a combined heat and power CHP generator to see how just making a CHP generator instead of a regular generator can save us both costs and make our system more efficient. So we need to set up that regular gas generator baseline first. So at the top here, just to be specific, I'm going to name this as my regular gas generator. And our technology decision here, we're going to leave it as consider for now, because we're going to have Xendee tell us if it's going to be optimal or a wise investment decision to actually invest in a generator, because it might not be a good idea. And I am going to set the max number as 1 because that's all the space our hotel has for. But of course, if your site can accommodate more generators or equipment, you can of course bump this up. Or you can bump this up to like a really high number so that it can consider as many as it needs. And what we're going to do for filling out the investment specifications and technical specification is we're actually going to pull something from our catalog. Of course, if you have your own generator or your own specifications in mind, you can always fill that out manually, but you can also pick something out from our catalog to save some time as well. So if you click on catalog, you're going to see several breakdowns of how to view your catalog. You can always view your own personal catalog, which is stuff you've saved for yourself, only for yourself to use. You have stuff from your project team, which is going to be stuff shared by your team members. You also have a Xendee catalog, which is like the global Xendee catalog. That's going to have a lot of common, like ready off-the-shelf generators or models. Or you can view them by all, which is just going to show you everything. And what we're going to do here is I've already shared a generator with this team, so our Microgrid class team. So you should be able to look it up. Just look up demo 200 kW And then you should see a result that says demo 200 kilowatt natural gas generator. And it should also say shared by Rita Chen, me, on your project team. So once you see that, you can select it. And that's going to directly bring in the information from the catalog into our window here. So again, we pull this from the catalog, and it is called the 200 kilowatt, or sorry, demo 200 kilowatt natural gas generator. So once you pull that in, you'll see we have its costs as well as technical specifications entered. And this natural gas generator is going to run on natural gas, so it's already selected in the fuel type. And remember, we are just going to model just a regular gas generator for now. So we're going to leave the CHP toggle as no. So this just means that it's going to act as a regular gas generator. It's not going to provide any heating purposes yet. We'll take that. We'll take a look at that in a minute. So once you have this pulled up, we can click save in the bottom left-hand corner to save our progress. And now you'll see that it's added a new icon to our map, the regular gas generator. And now let's go ahead and run an optimization. I'm going to name it something like consider regular gas generator. Again, I'm leaving everything else as default. I'm leaving the optimization decision as reduced cost. And then for the reference model here, I am going to select it as Xendee computed this time, which means that it's going to calculate its savings, so both its cost savings and emission savings against our existing baseline. Remember, our existing baseline is our existing assets, so our electric utility connection and our existing boiler and the existing electric chiller. And then we're going to go ahead and run the optimization. And then once you run an optimization, you can actually go ahead and make other changes and run a new optimization while your old one is still running. So at any given point, you have the ability to run up to 3 optimizations. So that kind of allows you to keep making changes and run new optimizations as you're waiting. So again, to summarize what we've done for this optimization is we've added just a regular gas generator because what we're going to do is we're going to compare adding a CHP versus adding a regular electric only gas generator. So while that's running, let's go back to our gas generator icon here. So you can double click on it to bring it back up. And what we're going to do now is we're going to now convert it into a CHP generator to see if it would bring in more savings. So at the top, I'm going to rename it to our CHP gas generator just so I can, tell the difference. I'm going to leave everything else as the same, except under the technical specifications here, I'm going to enable the CHP, the combined heat and power capability toggle. So what this is going to do is that in our optimized scenario, it is now able to output both electricity and heating. So, and then once you enable the CHP toggle, you'll see that we have a few additional inputs become enabled, and that is going to be our heat and power ratio, as well as a toggle for heat curtailment. I'm going to leave the heat and power ratio as the default, and I am going to leave the heat curtailment toggle on. So this just means that our excess heat can be curtailed. So for example, if my generator outputs this much for electricity, it is going to be able to curtail any excess heat that it cannot use. And we'll see this a little bit more in our optimization later. So again, I turned the CHP toggle on, and this brought in extra symbols, and I am going to let it be able to curtail excess heat. And of course, since we made that change, I need to go ahead and click save in the bottom left-hand corner. And you'll also see that our symbol on our map has been renamed to our CHP gas generator name. And then let's go ahead and run another optimization. So now I'm going to say, consider CHP gas generator as my optimization title. Leaving everything else as default. Let's go ahead and run an optimization. Okay, and our result for our previous optimization has completed. So let's take a look at that. Remember, you can access all your results from the results page at the top. So here's all our results. We have our result for our regular gas generator run. So let's look at that. Okay, so as we can see, Xendee has decided that adding a gas generator is going to be financially attractive for us. And we'll see on the left-hand side here a kind of quick breakdown of how much we're going to be saving. So we have our reference cost, and then our investment scenario cost. Of course, the investment scenario is going to refer to the scenario in which we've added our new gas generator. So as you can see, we have about 9.5% in annual savings per year, and just a tiny bit of emission savings. This is actually interesting to point out because our site, if we remember, is located in Georgia, which the utility emissions are probably going to be moderately high because there's not as much renewables. If this project were in, say, California, for example, where there's already a lot of renewables integrated into the utility production, you might actually see negative emission savings when you involve natural gas, just because the energy from the utility might already be cleaner. Okay, so let's go straight to our dispatch table. Of course, you can explore everything else in detail, but for now, we're just going to look at the dispatch to see where the new generator comes into play. So in our electricity dispatch, you'll see now, in addition to the electric utility purchases, our gas generator is going to kick on during some of the hours to deflect some of the electric billing, especially when it's more expensive. If we go to August, for example, you'll also see that change a little bit depending on the season. But the heating dispatch and the cooling dispatch are going to look the same because our regular gas generator is not going to be able to contribute to any of our thermal loads. So that's our regular gas generator. So just to recap, it does save us a little bit of money. We'll save about 9.5% as far as annual costs, but let's see if making this generator into a CHP generator will save us even more. And it looks like our optimization with the CHP enabled gas generator has completed. So let's take a look at that. So again, Xendee has also decided to invest in this CHP gas generator unit because it's financially attractive for us to do so. The biggest difference we're going to see here is that we're now going to get a lot more savings. We're going to get 19% savings in costs as well as emissions. So let's take a look in the dispatch to see where our CHP now contributes to multiple of our loads. So again, with electric dispatch, you'll see that it's going to kick on to just offset some of the utility electric purchases. And at the same time, since it's a CHP, every time it generates electricity, it's going to also produce waste heat. And that waste heat can then be used for part of our heating dispatch. So our heating dispatch is going to look very different here. Remember that before, all of its demand was just being met by the existing boiler, which was the red lines. But now you'll see that most of its demand is actually going to be met by waste heat from the CHP gas generator, or in this case, it's called CHP gas generator just here. And then we'll also see there's a dashed a line / color for heat dumped by the CHP gas generator. And this is going to represent the heat, the excess heat that's curtailed because there's too much heat production in relation to the demand. So remember that earlier when we set up our CHP generator, we enabled the excess heat curtailment toggle. So this is where it comes in, and that the excess heat can be dumped by the generator. If you had disabled that toggle or disabled the ability to curtail excess heat, what that would do instead is it's going to prevent the CHP generator from generating too much heat that cannot be used. So in this case, what it would do is it will only generate enough electricity so that all of the excess heat cannot be used. So essentially, it will be capping the amount of electricity that can be produced. And of course, our cooling dispatch has not changed because we haven't added anything that can contribute to our cooling dispatch. But that is what we're going to do next. So let's exit out of our results here and move on to adding some cooling technologies. So what we're going to do in the next step is we're going to progressively add more technologies that can potentially complement our hotel's heating and cooling system and make it more efficient. We are going to save the gas generator. So what we're going to do is instead of leaving it as consider now, I'm going to set it to forced, which means that I'm telling Xendee, like, I know I want this generator and you are going to install it no matter what, even if it's financially unattractive. But we know that it is financially attractive, so we are going to add this generator. So again, I'm setting it to forced and setting the number to 1 generator because that's all the room we have for it. If you are open to adding additional capacity, but still want to force that decision, you can set it to forced and more, which means that it's telling Xendee, I am going to add at least 1 generator, but I am going to be open to more generator if it's going to be optimal. But I'm going to switch it to forced. We're just going to exactly 1 CHP. So again, I'm going to save that in the bottom left-hand corner. Okay, I'm going to let everyone take a moment to catch up. Just to summarize what we have done so far is we've compared adding a regular generator, so just an electric-only generator, against a CHP generator, which is going to be capable of producing both electric and heat. Also, some of your optimizations might be taking longer than usual to run just because there's probably a bunch of us on the server right now running this exact same optimizations at the very same time. So there might be a slight delay, but usually if you're just working on your own time, it's probably going to run a lot faster. Okay, so hopefully everyone has caught up and are ready to move on to adding our cooling technologies. So from our bottom symbols bar here, we're going to add an absorption chiller next. So to click on the absorption chiller symbol, it's going to bring up a window for absorption chiller. So at the top here for technology decision, I am going to leave this as consider, because I want Xendee to tell me what the optimal size of the chiller should be. You can add a maximum size capacity if you want to limit its maximum install, but I'm just going to leave it as blank for now to not set an upper capacity. Again, you always have to define your investment specifications. I am just going to use the default values for now, as well as your technical specifications. I am going to use the default coefficient of performance, or COP, but of course you can change it if you'd like. And we haven't talked about this yet, so let's take a look at it very quickly as well. You can enter a non-linear curve for the coefficient of performance. If you click on the blue thumbprint button, it will bring up a kind of a table / chart for entering different COPs at different loadings. So by default, for every single loading, the coefficient of performance is always going to be the same. But if you have a nonlinear performance curve, you can enter in here. So for example, maybe your absorption chiller is more efficient at 100% loading, then you can change that here. And what you'll see is that once you enter in these numbers, it's going to automatically update this curve here just for a visual representation. And of course, if you made any changes, you can click save. But I'm just going to use a default. And also note that if you enter a nonlinear curve for the COP, or really for any of our options that have the ability to enter a nonlinear curve, like generator efficiency, temperature derating, the more nonlinear points or discrete points you add, that sometimes can increase your optimization runtime, just because it's going to be more equations for Xendee to solve on the back end. So once you have your absorption chiller all entered and happy, you can click save in the bottom left-hand corner. And now we'll also see we have our absorption chiller icon show up on our map. And once that's ready, let's go ahead and optimize. So now that we've added absorption chiller, I'm going to name it, something more specific, like 1 CHP plus consider absorption chiller, just so I can keep track of, oh, I'm not allowed to use that. Just so I can keep track of what I'm doing for each run. Again, I'm going to leave all of the other optimizations as a default. And then we're going to go ahead and run an optimization. Okay, once that is running, I'm going to let everyone take a moment to catch up again. Again, what we've done for this part is I've just added an absorption chiller, and I'm letting Xendee decide how much capacity to add to complement our CHP gas generator. Remember that we left our CHP gas generator and we're actually forcing the installation of 1 CHP generator now, because we know that it's financially attractive and we want to use it. And what the absorption chiller is going to do is it's going to be able to also use the waste heat from the gas generator, but it's now going to be able to provide cooling. So my result has finished. So let's take a look at the optimization results. So you'll see, again, over here on our investment decisions, we have our forced CHP gas generator, CHP gas generator unit, and Xendee has decided that 340 kilowatts of absorption chiller will also be beneficial to us. And then if we come and look at our savings, we'll see that we now have even more savings percentage. We now get almost 22% of savings. So let's take a look at the dispatch to see where the absorption chiller now comes in. So again, our heating is going to look pretty similar. We still are going to have both utility electric purchase as well as contribution from our gas generator. And the heating is going to look actually a bit different now because what this whole system is now going to comprise of, it's going to have, of course, the existing boiler that's always going to be available. It's going to have the waste heat from the CHP generator to meet some of that excess heat. But now it's also going to have a heat for chilling load. Because what that absorption chiller is going to do, it's going to convert that waste heat also from the gas generator into chilling. So now if we click on our cooling dispatch, we'll see that we now have two different types of sources for cooling. We have our cooling from our existing electric chiller, which is always going to be there. And then we have cooling from the absorption chiller, which is using some of that excess waste heat and using it for cooling. Now, of course, our CHP generator is now going to split its waste heat between heating and cooling. But Xendee is going to optimize that based on a combination of factors like our TOU electric tariffs, because remember that our electric utility tariff is going to be most expensive to buy electricity from the utility, especially in the evening hours. And remember that our default or existing electric chiller is powered by electricity, so it has to buy electricity from the utility if it needs to turn on. So what Xendee has decided in this case, it's that it wants to kind of mitigate using the electric chiller during the evening hours, because that's going to be the most expensive time to do it. So that's why it's kind of shifting some of its excess CHP waste heat into the absorption chiller, mostly during the evening hours. And you might also see the behavior change depending on the time of the year. So if we go to August, for example, where the cooling needs going to be higher, you'll see the cooling demand and more absorption chiller usage during that time as well. So now we have a lot going on. So again, please take your time to fully review your results and reporting so that you understand everything. Okay, so now that we've added our absorption chiller, we now have a complementary technology for all of our thermal demands. The one last thing we are going to explore is the addition of a cold storage. We also have an option for a heat storage, but we're just going to look at one for now. The cold storage, you can kind of think as of like a BESS or energy storage, but for cooling and heating. So again, the symbols bar here, I'm going to double click on the cold storage symbol, and that's going to bring up the setup page. Again, I'm going to leave the technology decision as considered because I want Xendee to tell me if and how much cold storage is going to be optimal for my site. I am going to leave everything else as the default, but of course you can change it if you like. Under the technical specifications, you're going to see that a lot of these inputs are going to be very similar to our typical electric batteries inputs. So you have your efficiencies, you have your charging rates or your C rates, a minimum and maximum state of charge, as well as annual cycles, but I'm going to leave those as default. And once you've done that, again, click Save on the bottom left-hand corner. And you'll see that we now have an extra symbol on our map for our cold storage. Okay, and to summarize what we did for this section, all I've done is I've just added a cold storage and setting it to consider. Again, I'm going to let everyone take a minute to catch up. Okay, so now let's go ahead and run another optimization. So we have a lot of technologies now. I'm going to name it something very specific and consider absorption, chiller, and cold storage. Again, I'm leaving everything else as the default, and I'm starting my optimization. And one trick is when you have a bunch of technologies is you may want to remove a technology from your model or like exclude it from optimization, but you may not want to delete it, like actually delete it from your model because you already spent a bunch of time inputting the technology. So what you can do in that case is you have two options. You can add it to your catalog, your personal catalog, and that allows you to quickly pull it back up. Or if you don't want to delete it from your model, what you can do is you can actually set it to forced and set it to 0. So this is going to be essentially the same as just omitting something from your model, but it doesn't remove it from your actual model. So, if you want to come back later and re-add it, you can then, change it back to consider or forced or whatever you were doing before. So just one neat trick when you have a bunch of technology icons going on in your model, but you don't want to delete it from your project. Okay, so my last result has completed. So remember, this is going to be our consider absorption chiller and cold storage result. So let's take a look at our report. And it looks like Xendee has, again, decided to invest in everything. So now we have our CHP generator, our absorption chiller, and cold storage. And now we get a tiny bit more savings at 22.7%. And you might notice that the capacity for the absorption chiller has actually changed. Just because with the addition of the cold storage, it might not be necessary to have as big of an absorption chiller as before. So let's actually go back and look at our size from earlier. So from our last result, we had a 340 kilowatt therms absorption chiller, whereas in the new case, we've decided to go with a very big cold storage and then a smaller absorption chiller. So let's take a look at the dispatch to see how now that plays out. So again, your electric is going to look pretty similar. You have your electric utility purchase as well as CHP generator contribution. And for the heating, we are still going to have the same components. So heat from your existing boiler, waste heat from your CHP gas generator, and then some that will be converted into absorption chiller for cooling. Remember that our absorption chiller is now a lot smaller in capacity. So this section, the heat for chilling, is now probably also going to be a lot smaller. If we take a look at August, where there's going to be more seasonal need for cooling, we will see that kind of fluctuate back up. Now let's take a look at our cooling dispatch. So now you'll see we have some extra components for our cold storage. So bear with me here. There's a lot of new symbols going on, but our cooling storage is going to be represented by this orange line for a state of charge, and it's going to correspond with the y-axis on the right-hand side here, the cooling availability / percent capacity. So this is kind of like the same as state of charge for a normal battery, or like how much the battery is charged. And as you can see here in the evening hours, when electricity is most expensive, this cooling storage is going to discharge pretty much all of its capacity. And the bright purple bars are going to represent chilling that's discharged from the cooling storage. And it is going to be charged during the off hours. So you kind of see these brown dash line here. That's going to be when our cooling storage is going to be charged. And it's going to be charged by cooling from the existing electric chiller. So you'll see in this section here, our regular demand is going to be the black line. So this is our actual cooling load, it's this black line. But you'll see that the blue bars, it very much overshoots the black line because it's also being used to charge the cold storage, which is designated by this brown dash line. So what's happening now is that the existing electric chiller is now also being used to charge the cold storage. And it's doing so in the off hours, remember, because that's when our utility electricity purchases is going to be the most affordable or the cheapest. And then, of course, in the evening hours when electric utility purchases is going to be most expensive, that's when we're depleting all of our cold storage. However, we are still going to have a little bit of contribution from our absorption chiller, which is this like light teal-ish color, just by using the waste heat from our CHP. And of course, if you go to August, you might also see some differences. Overall, the cooling demand is going to be a lot higher. And now if we go to our operation summary tab, we'll see that we have a few extra charts. We should have also looked at this earlier, but we also now get a generator operation chart, as well as on-site generation, which is from our CHP. And you'll also see a monthly emission summaries table. If you are an existing Xendee user, this chart is actually completely new, so you may not have seen this before. But you'll see that this is going to summarize where our emissions are coming from, both for CO2, which is on the left-hand side here, and NOx, which is on the right-hand side. So you'll see that most of our CO2 emissions are going to be coming from our electricity utility purchases, and then some are going to be coming from our natural gas usage. And then the purple line is going to be our NOx emissions, which is going to be from our natural gas. And then at the bottom, we'll see our technology capacity factors for all of our different technologies, as well as the annual number of cycles for our cold storage. As you can see in the dispatch, we are using the cold storage almost every day, so it has a very high number of cycles. Okay, so that is pretty much all I have for the demo portion today. Just to recap what we did, what we've done for this project is we've added, in addition to your typical electric load profile, we've gone ahead and added cooling, space heating, and water heating to represent the thermal needs of our site, which is usually going to be what you need for a comprehensive energy look at your site. And then from there on, we took a look at our existing boiler and existing electric chiller, which is what we are assuming to be the existing on-site technologies that meet our cooling and heating demand. And from there, we added some new technologies, including our CHP, combined heat and power gas generator, which contributed to both of our electricity and heating profile demands. From there on, we added an absorption chiller, which further complemented our site DER setup by also using that waste heat for cooling. Lastly, we also added a cold storage unit, which enables the cold storage to be charged up when the electricity is cheapest during the day, and then discharge when the electricity is going to be the most expensive at the evening. So again, I know we went through a lot today. If you are new to Xendee, I highly encourage you to go through our on-demand resources as well as guided walkthroughs for more detail on how to set up a project from the very beginning all the way to the very end, and all the necessary components that usually go into a complete model, like financing, and everything else we didn't cover. And of course, you have this Xendee trial through 1 whole week from today. So please take advantage of that and explore other technologies in Xendee, other analysis configurations, reporting, or even try out a different sample project of your own. If you have any questions about how to use Xendee, feel free to reach out to me or Lulu, and we'll be sure to help with that. And yeah, I'll hand it back to Lulu.
Thank you, Rita, for that great demo. And thank you, Ray, as well, for helping with the Q&A. That was all for today. Hope this was helpful. We'll be sending out an email with the recording probably tomorrow. And yeah, we'll also keep you updated about further trainings. Thank you all so much for joining. Have a great rest of your day.